So we covered a few statistical approaches, and now we're going to look at a proximity-based approach. So distance-based and density-based, so those methods does not form clusters. They try to find outliers based on the intuition of outliers going to be further away. Outliers may be less dense or more dense. There's distance-based outlier detection method. So basically, those group of methods look at the distance. Object O is an outlier if its neighbor does not have enough other points, its distance away. Density-based outlier is outlier if its reachability distance is relatively much lower than its neighbors. So the area this outlier resides is going to have much less dense neighbors. So we're going to look at distance-based outlier detection, this one method first. So a bit of definition. We have a set of parameters here. So in this distance-based outlier detection, we need to define this user-supplied threshold, R. R is the number of other objects in the neighborhood of O. And also we need another threshold, I. So pi is basically saying within the R neighborhood of this O, how many data points are there? We need the data points, the proportion of the data points of the entire data set in O's neighbor R has to be greater than this, pi in order for that object to be considered a normal object. If this dot has within its R neighborhood, it doesn't have this many dots, its proportion to the entire data set, then it is considered a DBR pi outlier. So to do such detection, it's a simple nested loop algorithm. For any object I, we calculate its distance from other objects. We count until R, the closest R neighborhood is reached. We count how many objects that we found. If the pi times n other objects are within R distance, then this inner loop is terminated and R is not, the object O is not an outlier. Otherwise, O is an outlier. So the algorithm is constructed this way because we know that majority of the observations are not outliers. So vast majority of the data going to terminate in the inner loop very early. Therefore, even we see a nested loop, oh, it's an n squared complexity. In effect, this algorithm actually runs linearly. So it's quite efficient. It's very simple. Just detect how far the R's within the R's neighbor, whether there is certain number of threshold points are there. So intuitive understanding of this, basically the distance between O and its case neighbor, whether that is greater than that radius parameter that we have. Do we have questions on this? So this algorithm, although it's efficient, there's further improvement on the algorithm. It's the thoughts is interesting. We see earlier algorithm is actually quite efficient, but it can be made more efficient. Adds a bit of complexity in terms of the computational steps. So here the method is called SAIL. Earlier, our distance-based method is basically we check every object and its R neighbor, and to see that whether it's very, very distant. This SAIL method do it in a more efficient way. It does not check every object. It doesn't check all its neighbors. So it actually put the data into groups. So again, data is partitioned into grid. And each dimension, length of each edge of a cell, so this is here, is R divided by, we need to first define R. R is the distance threshold that we mentioned earlier. This is a user-specified threshold. If we define length of each edge of the cell this far, then we know that each cell, this is a cell, has a diagonal length of half R. Okay, so we need to remember those. We need to partition the dimensions so that every data cell has a diagonal length of half R. Okay. Then for every, so we're not going to check those data points by points, data observation by observation. Instead, we're going to check them area by area. So every unit, every little cube. So for every little cube, we say that all the neighboring cubes are within the level 1 cells of cell C. And the next two layers or levels, the cells that's 1 or 2 units away from this cell will be considered its level 2 cells. Okay. Based on this distance definition, we know all the cells in cell 1 has to be close to C, and the distance must be smaller than R. Right? And we know those points, the distance of the data points to any of those data points in C going to be exceeding our threshold R. This is the setup. And then based on that definition, we can prune level 1 cells. We can process this data points cell by cell, not data points by data points. If the C, the number of points within C and its level 1 cell, all the data points counts add up together is greater than pi, that threshold that earlier we defined, the proportion of the data within this R neighborhood, times n. So this, if there's sufficient points within this part, within this 1 and the C area, then all the objects in C are not outliers because they have enough of points surrounding it within its R neighborhood. then we can do the definition of level 2 cells also gave us convenience that if all the data points within this level 2 area and the 1 and the C add up together, still not meeting the threshold, then every data points in C are outliers. So therefore, for a lot of data points that we can either keep them as not outliers, no, I should say either. So the data cells meeting those two standards will all give us clear decisions whether those data points are outliers or not outliers, so they can be easily processed. Here we're using the word prune, so that they're not being considered. We can process those quickly. And then only those data cells in between doesn't meet any of those conditions will have to be individually checked. That will give us some efficiency gains. But the idea, again, it's the same idea. We're seeing the R neighborhood, how many data points are there, or alternatively, whether the k nearest neighbor actually is within the R distance. So the cell method, yes.
Quick question. So if pruning one level cells is true, then we don't have to do pruning level 2 because obviously they're not outliers, so we don't have to check if they're outliers.
Mm-hmm. Yeah, definitely. Yes.
Sorry, I'm wondering, like, the goal is, as you said, to make it more efficient.
Mm-hmm.
Would this, how would this fare versus if we just use the previous method and maybe
they're going to give us exactly the same result.
Same result? Okay.
Yeah, exactly the same result. It's just the cell method is more efficient.
So if you use the previous method and use some kind of index, like a R3 index, would that be similar efficiency or?
Well, I don't know. I mean, you have to present the complete algorithm before we can actually talk about the complexity. So here, a linear algorithm is very efficient already. So the reason I think cell is interesting is just to give us a thought in terms of how to process large data set. That you don't have to consider. This idea comes out earlier. You don't have to consider data points one by one. You consider them group by group or clusters by clusters. So yes, cell probably going to be a bit faster than the simple algorithm that we presented, but the simple algorithm is already quite good. You can continue improve the efficiency. This is one of the questions that I remember when I was doing I was a student in that PhD seminar, and we were discussing what kind of research question is worth pursuing. Our professor at that time was saying, if there is a known algorithm that's efficient, then this problem is no longer worth pursuing. Half of the class agreed with the professor and the half of the class don't, because in their mind, there are always ways to make the efficiency more efficient, right? But yeah, I think making efficient things more efficient is great. But there are so many other open questions that needs people's bright mind. So I don't know. But I can tell you this two algorithm gives you exactly the same result. There are some efficiency gain if your data set is really huge. Okay, good question. I mean, question will wake us up a bit more. Thank you. So keep asking questions. Density-based outlier detection. Gosh, we'll have look at those formulas. It really make people sleepy. I don't blame you. So the density-based outlier detection, this idea is to compare the density of outlier, the neighborhood of this density, neighborhood of outliers density to the neighborhood of non-outliers. The assumption is non-outliers probably going to have more dense areas. Their neighbor going to be closer to them. Okay. So the intuition, okay, it's included here. So the method, we will compute some measures to measure the relative density of an object, then compare the relative density of that object to the relative density of its neighboring objects. For that, we need to introduce a number of, again, terminology. K distance of object, it's written this way, it's a distance between O and its case nearest neighbor. And the K distance neighborhood obviously are the points within that neighborhood. So all the objects, all the objects with that's closer to O than its case nearest neighbor are within case distance neighborhood. And NK could be bigger than K, since multiple objects may have the identical distance to O. Could. So it's not strictly smaller. That is a very minor detail. You really don't need to know. And then we define the reachability distance. The reason we define the reachability distance is because we want to define some other things and then compare it. So local reachability density is what we're really looking for, is what we're going to compare. Compare it with the O's, this is neighbors, and then come up with the final local outlier factor score, okay? So the reachability distance from O prime to O is, it's either the distance of O to its case neighborhood, we call it what K distance. It's either the K distance or the distance of O to its neighbor, whichever is greater. Again, this reachability distance is asymmetrical. Then we can define the local reachability distance of O as this. If you put this score in an inverse way, it's probably going to be easier for you to see. This is just the sum of all the reachability distance of O to its all the neighbors, then normalized by the number of neighbors, okay? And we have local reachability distance. So outlier is going to have a high score for local reachability distance or low score. So the outlier's reachability distance probably going to be greater, right? Therefore, this score going to be smaller, right? Okay, we're all sleeping. It's okay. So then we can actually define the local outlier factor. What we do is, again, to normalize this, for O, we look at O's local reachability density and compare it to the neighbors, its neighbors. Okay, we sum this up and we normalize it. The lower the local reachability density of O, the lower of this value, the higher the local reachability density of the KNs. Okay, so the lower this value is, the higher that value is, then we have a higher this value, and this indicates an outlier. So the outlier have lower density than the density that its neighbors have.